Okay, I think it's time. Let's get started. So my name is Gang Tam. I'm a associate professor in the Department of Computer Science and Engineering. So it's my great honor to introduce Professor Greg Morrisett from Cornell. So he is a Dean of Computing and Information Sciences, and he also previously taught at Harvard and also in the Computer Science Department of Cornell. So in addition to being the Dean of Cornell CIS, Greg also has many other titles. Let me just mention a few. I don't have time to enumerate all of them. He is an ACM Fellow. He is on the NSF Science Advisory Council and also on the Computing Research Association Board. Okay. So Greg's research interests are in programming languages and in applying program language techniques to building secure, reliable, and high-performance software systems. And he has made a tremendous contribution to the program language field. So I remember when I was a first-year graduate student, the first paper my PhD advisor gave me was one of Greg's well-known papers on typed assembly languages. So. And besides being a prolific researcher, he's also a great mentor. His PhD students and postdocs have gone on to join faculty in strong computer science departments, including University of Washington, Carnegie Mellon, MIT, University of Pennsylvania, Princeton, and University of Maryland, and others. I also personally benefited from Greg's mentoring. So when I started as an assistant professor in Boston, so we started a collaboration. So we have authored many papers together and secured multiple NSF grants. And I have to say, I cannot overemphasize the importance of Greg's mentoring over my academic growth, both intellectually and professionally. So to all the young PhD students here, I hope you all will meet your Greg Morrisett one day. Okay. So without further ado, let me introduce Greg.
Thank you, Gan. Appreciate it. Hi, thank you so much. Can you hear me? Is the mic on? Good. Thank you so much. What Gong doesn't tell you is the secret to mentoring is to just go find really smart students and smart colleagues and let them do all the hard work, and then you take all the credit. So you know, that's the way it typically works, at least in this case. It's a real honor to be here. Thank you so much for inviting me. I find Penn State and Cornell have many things in common. The feel of the towns are very similar, and the excellence in engineering and computer science, and in particular a focus on security, is something that both places really value. So it's a great honor to be here. Thank you for having me. I wanted to talk about some work that's going on, not just in my lab, but in other people's labs across the country around formal methods and proof engineering for secure software systems. And to motivate this, it's not too hard. Every time I've given a talk, I give a slide like this with headlines, and you can just Google for headlines, and it's really easy to find them. You know, the latest one is the Spectre and Meltdown kind of problem that we've encountered, which just goes to emphasize we don't know how to build secure systems yet. Whether it's, in this case, challenges at the hardware level or more commonly at the software level. This is a slide that I stole from some colleagues at DARPA that emphasizes it from a different direction. This is plotting the size in lines of code of two different software families. One family, that's the flat line down here, is the size of the typical malware that's used to infect systems. And that stayed relatively constant at about 100 lines of code. Whereas the lines of code that we're spending on software to try to protect systems is increasing exponentially. So that just sort of gives you a feel that as defenders, we're trying to do exponential amounts of work against attackers that are doing essentially constant work. So something is going very wrong here. Another thing that's kind of scary is that these software systems that we're introducing for security often just increase the attack surface of our settings and our environments and introduce new vulnerabilities. So we don't seem to be making a lot of progress. Now there are lots and lots and lots of things that need to be fixed. And I was talking to Trent, I'm going to say Yeager, sorry, this morning about, for example, configuration and operational issues in security are one of the biggest hard problems. But other things like underlying architectures, the design of systems really has to be rethought from the ground up in order to make them secure. Everything from user interfaces to the protocols that we're using, all of them have to be thought about from a deep security perspective to get things, to move things in the right direction. And there is no silver bullet. There's nothing out there that if we could do that one thing, that would fix all of our problems. But there is one issue that I think dominates where we spend a lot of our time and where the most bang for the buck is in terms of trying to secure systems, and that's in trying to eliminate bugs from software systems that we develop. Okay, so we may not get the specifications right, but if we can at least get the bugs out of software that we're constructing, then that's a step forward. That's a substantial step forward. So what's going wrong with the way that we develop software now? It's just not the case that we can develop substantial software systems without introducing lots and lots of bugs. You know, on average, they say about a bug about every 1,000 lines of code. So why is that? Well, one is that the processes that we use don't incentivize us to eliminate bugs. Right? We really haven't. I mean, if you're a company like Microsoft, you don't earn money by carefully pouring through your code and looking for bugs. You earn money by putting new features in and selling a new product. So there hasn't been that sort of incentivization. And particularly in the security world, the certification processes haven't really been based on the right things. They're often based on who developed the code, who had access to the code, and who developed it, as opposed to, is the code correct? And frankly, in the age of open source software, or software that's developed perhaps in a mix of China and India and Europe and the US and Russia, how can we assemble that in a way and have trustworthy code? So this idea that we should certify code based on the provenance, where did it come from, as opposed to what will it do when I run it, is a really misguided idea. And yet most of the military certification standards are really focused on that. Another issue is that current automated defenses are often really worse than we think they should be. So a simple example is something like intrusion detection systems or virus scanners or this sort of thing. Virus scanners really are based on the syntax of known attacks. You know, we look for bit patterns that match known attacks, and then we try to go down. And we may do a little bit more intelligence, but what we really want to do is match on the semantics. Find out, is this a piece of code that's going to do damage to our system? And to do that, we really want to understand the semantics so that if the code does it, but it's obscured in some way, we can discover it. And they also introduced new classes of vulnerabilities. As I mentioned earlier, there was one study, again by some folks at DARPA, that showed top 10 CVEs, and something like 5 of them were in antivirus and other products intended to support security. So a lot of things going wrong here. So what should we do to dig ourselves out of this mess? What can we do? One idea, and this is something that Gong worked on when he was a graduate student, something that I was captured by 20 years ago, is this idea of what we call proof-carrying code. So right now, when I hand you a piece of code as a code supplier, the obligation is on you to look at that code and find out whether it will do what you expect it to do. Whether it has some backdoor or whatever, that's up to you to figure out. And it's hard to do that when I just give you a binary. What if we could change the world so that code producers had to present to you some code, and we had a magic tool that could say, given a policy, whether that code would respect the policy when run? That would be the ideal world. Unfortunately, any reasonable policy that we may hope to enforce will be hopelessly undecidable. And analyzing binaries is also extremely hard to do, as some people here know very well. But if we could do this, and we could do this in a way that the checker was something that we trusted, this would be a step forward. So there's a slight shift in perspective for how to do this, and that's to just shift the burden of analysis and proving that the code does what it's supposed to do from the code consumer to the code producer. So this picture here, and I'm sorry you can't really see with the red here, but this says we have untrusted code up at the top coupled with a proof, a mathematical object that says this code respects a given policy. And then we have a proof checker over here that simply compares the proof against the code and makes sure that it's a valid proof with respect to the rules of logic. Okay? And all we've done here is shift the burden of analysis and proof from the code producer to the code consumer. From the code consumer to the code producer. Okay, so this model is called proof-carrying code, and George Nekula introduced this in his PhD thesis in the late 90s. It's an old idea, but he was the first one to really propose to use that in a security context, and they built a lot of interesting systems around it. At the time, though, they were doing really simple policies, like memory safety for, in this case, it was a Berkeley packet filters being embedded into the kernel. They wanted to know that the programs would terminate and that they wouldn't access parts of memory in the kernel that they shouldn't access. And so they were able to use this idea to demonstrate that as a proof of concept. Okay, one thing that I need to clarify is, what do I mean when I say a proof? In computer science, well, in mathematics, a proof, right, you all did these proofs in your math class. You'd write down, okay, this follows from that by this rule, and this follows from that by that rule. And often, if you weren't really sure, you'd say, oh, and by a leap of imagination, we get down to this conclusion. Maybe I always used to draw a little magic cloud with a lightning bolt and say, that's the justification for this step here. So that's a mathematician's proof. Lots of high-level sketches or details of how you reason about and get from one statement to another. A computer science proof is much more rigorous. The idea is it's a data structure. It's a tree where the conclusion is an instance of a rule of your logic. So I might have a rule that says, for example, equality is transitive. And I can conclude that x equals z, and that might be the root of my tree, the proof that I'm trying to prove. All I have to do now is provide proofs that there is some y for which x equals y and y equals z in order to use that rule to establish that x equals z. Okay? And to establish x equals y and establish y equals z, I build proofs of those things using instances of other rules. So the instances of rules are sort of shapes, and we string these shapes together into a tree. And what a proof checker is something that crawls that tree and makes sure that you only used valid rules and valid instances of those rules, and that the conclusion at the root of that tree is what you're trying to prove. Okay, so those are the steps. So when we talk about proofs in computer science, we're much, much more rigorous and formal than mathematicians. Okay, so, and the reason this is important is that constructing proofs or doing analysis on code is really, really hard. Okay, it's as if I gave you this maze, and imagine it was an infinitely wide maze, and I said, prove to me there's a path in here that goes from up there where there's a little hole to down there where there's a little hole. Well, now you have to do a lot of work, right? In fact, you may have to do infinite amount of work to go off to the edges. But if I give you the path and say, verify that there is a path here, a valid path, then that's something that you can do very easily. So that's what I'm trying to do, is shift the burden from the code producer handing you the code and you have to analyze it and prove that it's okay, to the code producer handing you code and a proof that that code respects some desired security policy. And this gives rise to an area that I call proof engineering, because really we didn't make any hard problems go away by this. We just shifted the burden of constructing proofs and analyzing things from the code consumer to the code producer. And building proofs, it turns out, especially computer science proofs, is much, much harder than people initially realized. The idea of doing this is an old one. It goes back to the 60s. People like Tony Hoare and Edgar Dijkstra and so forth were championing this idea back then, not for security, just for program correctness in a sense. But they were pushing that idea, and it's taken until this time for us to start to realize that. And what's emerging is a new discipline. It's analogous to software engineering that we call proof engineering. And the challenges are, how do we construct proofs at the kind of scale that we need for real systems? How do we have reusable components? How do we have the right abstractions, the right languages for expressing those proofs and so forth, the right logics for reasoning about things, in order to make this an enterprise that we can do. And that is an emerging discipline in a sense. But it has strong connections to software engineering. Okay, so as I said, it's not a new idea. These are two Cornellians, Bob Constable and David Grease, who worked on this idea. And so you might ask, oh, by the way, this is also Vladimir Voevodsky, who was at Princeton. He just passed away this year. He was a Fields medalist. He was trying to do for mathematics what I'm trying to do here for security. What had happened was he wrote some very detailed proofs in, I forget, algebraic geometry or something, some very intricate things, and then realized that he had a bug in the paper. And he started to doubt his results. And in fact, he went back through 2 or 3 papers and found more bugs. And so he started to think, oh my God, maybe we're building a very shaky foundation for mathematics. Maybe we're proving the wrong things because we've made mistakes. We have bugs in our proofs. So he started also working on proof engineering in the context of mathematics. It's not just security that's doing this, but now also people like Voevodsky. And it's a real shame that he passed away just so recently. So what's changing to enable this? A couple of things. One is tools for supporting the construction of proofs automatically, at least fragments of that tree automatically, are becoming much, much better. And an example is SAT solver, so satisfiability solver. These are basically just taking Boolean formulas and trying to find a satisfying assignment. We were all told this is NP complete, right? You can't solve this problem. No, you can solve it, okay? And there's that is sometimes. And there are now great SAT solving tools. This graph plots the improvement over a stable set of problems in SAT solving performance over a number of periods. And the thing that I want to emphasize is this is not due to hardware speed up. This is running on the same hardware. This is all because of algorithmic improvements over the last 10, 15 years in SAT solvers. So SAT solvers, SMT provers, those are satisfiability modulo theories provers, have also advanced dramatically. They make it easier to construct some proofs, some fragments of proofs in a fully automatic way. And that helps and enables things. But the thing that I'm most excited about is in the last few years, we're starting to see academic projects that really use this idea of constructing a formal proof of some correctness or security condition come to fruition. And so an example is in the compiler arena. Xavier Leroy at INRIA has developed a C compiler called CompCert that maps C down to at least 3 different architectures. It's mildly optimizing, like GCC 01, but he has a proof of correctness for the whole compiler. And that says that if the C code at the source level would behave some way, then at the target level, if it would behave that way, then that behavior could be found at the source level as well. And so what does that mean? That means that if you reason about the source level, if you prove a safety property about the source level, then that safety property will be preserved at the target level on the machine code. This is a real major, major breakthrough. This was, by the way, Tony Hoare posed this as a grand challenge back in 2002, and Xavier fixed this in 2006. So we're really making progress there. Another example is in operating systems. So at NICTA down in Australia, they developed a kernel called SEL4. SEL4, they built a functional specification. It's an L4-based microkernel. They built a functional specification and proved that the code that's running on the machine respects that functional specification. And then on top of that functional specification, they proved some security properties like non-interference for different processes that are running in different address spaces. So more recently at Yale, Zhang Xiao has done a system called Certicos that proves the correctness of a multi-threaded kernel. And the thing that I want to talk about in terms of advancements is SEL4 took 20 person years to develop the proof. 20 person years. And this is a small kernel. We're talking about, you know, a few thousand lines of code, not the millions of lines of code that make up Linux or Windows or something like that. So it took 20 man years. Zhang managed to prove the correctness of Certicos in 20 person months, right? So, and why was he able to do that? It's because of actually advances in program logics for modularly reasoning about different components of the operating system and being able to snap the proofs together. All right, so we're making progress not just on algorithms and tools for constructing proofs automatically, but logics and languages for thinking at a higher level of abstraction. And there are some other examples down here. I'm going to talk a little bit about the world of crypto because I've done some work in that space and work on proof carrying code in that setting. But let me highlight one other big thing that really brought this to my, that told me that we're really on the threshold of something big breaking through. So DARPA ran a program called HACMS, High Assurance, I don't know what it stands for, HACMS, it sounds cool. Okay, but it was a program where they took a drone like this one here, and they looked at the software stack, and they gave it to a red team, and they said, okay, suppose we're flying this drone over bad guys, could they hack into it? And sure enough, it was trivial to hack into. They found like 75 different ways to hack into this off-the-shelf drone. Okay, so they hired a bunch of academics and people from companies and so forth and said, okay, clean slate, build a new software stack from the ground up so that we can't break into it. Oh, and oh, by the way, we're not just going to run it on that little drone, we're also going to run it on this big drone. So this is some kind of autonomous vehicle that the Army was developing at the time. So they did that. The PIs did this. They built a clean slate software stack. So for example, at the base of that stack is that SEL4 kernel that has been proven correct. They used a lot of language technology to avoid having to construct proofs, that is, generate things that were provably correct by construction. They integrated all this and proved a number of system-wide properties, like the system is memory safe, that the system always ignored malformed messages. That's a significant source of bugs in most systems. That it wouldn't execute something unless the message to do so was authenticated, and so forth. Okay, one of the challenges is, though, they didn't model the sensors and the actuators and whether things were correct at that level of abstraction. They're just looking at the software stack. But even so, this is great progress. And part of the reason I think this is great progress is they gave this red team, and these were some really good hackers inside the Army. They gave this red team this software code. They gave it all to them, the software, the source, and said, okay, find a way to break into this. And for 6 weeks, they tried to find a way to break it. These guys are good. They know how to break into systems. They couldn't find a way to do it. Okay? So that, I think, is a first. It's very hard to think of another system. It's usually the opposite story. Usually the story is I give you a system, it's small, it's stupid, I've thought about it really hard, I can, you know, and I give it to you, and then some guy breaks it tomorrow, or some woman just absolutely crushes it. So anyway, it's anecdotal evidence, but nevertheless it's strong evidence, in my opinion, that this approach actually does lead to higher assurance for software systems. Okay. In fact, one of the experts, a guy I know very well, said in a write-up, this is the most secure UAV on the planet. And the fact that that's true terrifies me because there are a lot of UAVs that military systems are building at this point. But at least DARPA and the US Army is starting to wake up to this. Okay, still many hard challenges. As I mentioned before, SEL4 took 20 person years to develop. Another example is CompCert. As a compiler, the proof of correctness was about an order of magnitude bigger than the software itself, the compiler itself. So this becomes the tail that wags the dog in the following sense. If you want to update CompCert, you have to update 10 times as much proof in general to get that to work right. So another issue, and I mentioned this earlier, models of the environment have to be faithful. If, for example, you want to rule out subtle security errors like timing channels, but you don't model timing in your statement of correctness or whatever, or you don't have accurate models of those things, then you're never going to use this methodology to help solve the problem, right? And this is a really hard one. And then we need some way to handle legacy code, because there's no way that we can afford right now to sit down and prove the correctness or the security of every piece of software that we write. We need to reuse existing code. So we need architectures to contain that code and isolate it in some useful way. Okay, one field that I think is very ripe for this idea of proof engineering is cryptography. And really, if you go back to something like the heartbleed bug, this was, you know, where a developer, well-meaning developer, just left a debugging command into the OpenSSL library that said, basically I could send a message that says, hey, please echo this message back to me. And oh, by the way, the message is 4K. And instead of sending you 4K, I only sent you 1 byte. And then the server would dutifully respond and respond with 4K. That 1 byte followed by all the memory that just happened to be in the server at the following locations. And so that was a great way to peek into the secret memory of the server and leak out keys. We have no idea how bad people were able to take advantage of this. But Bruce Schneier, you know, I love this quote. He said, Heartbleed wasn't just catastrophic, you know, it went to 11 on the scale of things that we should worry about. Okay, and one of the other reasons I think crypto is so important is auditing. That we really need smart people to go through and audit crypto code. It's very hard to find people to do that and to incentivize them to do that and to look at the whole system. So in this case, this is the OpenSSL library. Everybody's using this. Everybody. And some guy just left a debugging command in there. Okay? We can't rely upon the open source community to actually do an adequate job of auditing security critical code, as evidenced by this. So somehow we need different mechanisms. And if we had a proof that OpenSSL only accepted this set of messages, only did these kinds of responses, and had certain security properties associated with those responses, then we never would have been able to update the proof if we'd made that change to the code, right? It would have, either we have to change the specification to admit that behavior, or we'd have to reject the code. Okay, so in addition to coding errors, if you look at modern crypto, the community has sort of raced ahead. They're kind of like the mathematicians. They're doing these paper and pencil proofs of systems that are really important, but finding out after the fact they're nowhere near as secure as they thought they were. So there are various flaws, and here's a couple of quotes that I think are telling. Our field may be approaching a crisis of rigor, and we generate more proofs than we can carefully verify. So I think this is a field that is ripe for proof engineering, where people who work on formal methods should be working with cryptographers to develop formal computer science proofs that protocols do what they're supposed to do, and the code that implements those protocols does what it's supposed to do. So that's what I've been working on with my students, is around mechanized proofs of security for cryptographic schemes. So instead of a human having to audit the code, we can have a machine check the proof automatically, and with a very simple, small, trusted program. So that also forces the community to start to standardize on definitions. If you read any crypto papers, there are always very subtle differences in the setups of the formalisms that go in those papers, and they make a big difference at the end of the day. Standardizing, having language to standardize those assumptions would be useful. Maybe more importantly, we want to couple the formal verification of the cryptographic protocols to the actual code. We want to be proving properties about the code. Otherwise, if we're just proving properties about models of the code, we're going to miss the kind of heartbleed bugs where somebody leaves a debugging routine in there. And finally, we need verified compilers, because you don't want to reason about the crypto code at the level of the machine. You want to reason about it at the source level. And we need to make sure that the cryptographic properties are preserved when we translate from the source level to the target level. But typically, a compiler correctness proof only talks about refinement. And refinement preserves some properties, like safety properties, but not other properties like, or non-properties like non-interference, which is an important confidentiality property. The way to do this is through a new kind of compiler called a fully abstract compiler that really came out of programming language semantics. And I won't have time to talk about that, but there's a lot of interesting work going on in that space at places like Northeastern. Okay, so mechanized cryptography, like I said, the goal is no one needs to trust the proof of security. If you think about it, I think this is really enabling for open source and also for cooperation amongst different nation states. Right now, if, let's say, somebody in China developed a cryptographic algorithm, there's no way the US government would adopt it because they'd be worried there's a backdoor. Same thing with the NSA developing something and trying to send that to China. Well, what if I could give you a proof that there's no backdoor? Then that's a basis for trust. Okay, so there are two basic models that have been used for formally reasoning about cryptography. One is the kind of algebraic symbolic approach that a lot of people have done in the past. That's great work. Dolev Shao is the typical example. Part of the reason it's great is because it can be automated quite a bit with SMT provers, and it's at a high level of abstraction, but the problem is it can miss details. And a simple example is in one of the authentication protocols that they were trying to verify, they missed the fact that the protocol was leaking the length of the messages that were being sent back and forth. And that actually was a flaw that somebody could exploit. So the other way to do it is really computational. This is what the cryptographers do. They consider the probabilities, that is, I want to be able to say with high probability, the attacker cannot break this property or can do so with only a very, very small probability that I can control, right, through a security parameter. So there's some early work on this, and the ones that I think are most influential are the work on EasyCrypt and CertiCrypt. These were developed by people in France and in Spain and so forth. Gilles Barth and Bruno Barras and a few others. They were basically programming language ways to express cryptographic protocols and then give a semantics to them as probabilistic systems and then try to prove them that the systems met certain security properties. So there are a lot of good things about these, and they really were the first attempts. EasyCrypt was just intended to be easier to use than CertiCrypt. It used a lot more automation. But I had a student who was actually working at Lincoln Labs who wanted to prove the security of something that I'll talk about in just a second. And he and a team of cryptographers and formal methods people tried to use CertiCrypt and EasyCrypt to do this. And the goal was to prove the security of a private information retrieval protocol, a searchable symmetric encryption protocol. And the outcome was a partial success. They could prove most of it, and they did find minor flaws in the implementation, but they got stuck on certain results. So this is the student, Adam Petcher. He went off and designed as his PhD thesis a new framework for reasoning about cryptography in a formal fashion in the Calc proof assistant. And he developed a formal language for expressing cryptographic games, protocols, and so forth. The language has a semantics that allows us to reason formally in the way a cryptographer does. And from the model, we derive a program logic that is similar to what they used in CertiCrypt for reasoning about things. But because we have an underlying semantics and the logic is on top of it and derived from it, if we don't have enough rules in our logic, we can derive new ones from the semantics itself. And that was where that avoids us getting stuck the same way that they did with CertiCrypt. Okay, I'm not going to go through this in detail. You can ask me. I'm happy to talk about it at some other point. But this is the little programming language that we're modeling. It really only has a handful of commands. One is return A just means, okay, A is a pure functional expression of some sort, and I just want to return that value, okay? This command, X gets C followed by F of X, is just like semicolon in a normal language, but it lets you bind a variable to a resulting value of a computation. Those aren't unusual. This third command is the only thing that's a little weird. It lets you pick a uniform, pick a vector of bits uniformly at random. Okay, so it evaluates that. And so the semantics of these probabilistic languages is just that. It gives you a probability distribution over the discrete elements that we're computing over. Okay, so just as an example of a little program expressed in Adam's framework, here's the definition of a one-time pad. So remember, a one-time pad, you just take a key, just random bits, and a message, and you just XOR them. Okay, and that's exactly what this says. It says given a number n that's a nat and a message that's a bit vector of length n, I first pick a random bit string of length n, and then I XOR that with the message and I return that. Okay, and one of the things that you can do with Adam's reasoning, the semantics, is prove that no matter what the message is, the probability that you get a certain bit vector out is, 1 over 2 to the n, right? That is, it's complete because the choice is random and because XORing essentially destroys the information. Okay, so that, obviously that's not what you do in these big things, but it gives you a feel for what's going on. Okay, more generally, you write down security definitions as programs in this probabilistic language. These are called games. And you set up your security conditions to say an adversary should win the game, should not win the game, unless some very small probability, that is, they guess the password with very small probability. So in the example we saw with the one-time pad, they might guess that the bit string was the particular key that you chose at random, and we have to account for that in the formalism of the proof. We can't just say they won't learn the information. They might guess it, right? The difference is that we say, well, the probability of them coming up with that answer is small. And we also restrict them in a computational sense to polynomial time. Okay, so I'll skip over this too. This is just an example. But often what we do is set up this impossible system that we want to prove some probabilistic fact about. And then we simplify that system, rewrite it over and over and over again, using a program logic to justify the statements as we're moving from one to the other. And this is called game hopping, where we're making a reduction from one argument to another argument. This turned out, I'm a compiler guy at heart, and this turns out to be nothing but compilers and compiler correctness. So it was actually something that I understood quite well. I won't go into that either, but this gives you just an example of the kinds of simple rewriting that goes on in these programs. For example, if I say let x be, well, first let y be the value of C1 and then run C2, so x is going to get C2's value while y is a local variable. Well, I can reassociate that into let y be C1, let x be C2, and then C3. Okay, so that says that this sequencing is associative. It's also commutative when C1 and C2 are independent. That is, if C1 and C2 are only drawing independent random variables, then we can commute them. And so that's the kind of equational reasoning that you can do about these probabilistic programs, is show that this program is equivalent to that program, and so forth and so on. Eventually you get down to a program that's impossible, or under some assumption, for example, that I know how to factor prime numbers efficiently, big numbers into their prime constituents efficiently. Making that assumption as being a hard problem, then I show that, oh, this would give the attacker a way to do that. Okay, on top of, oh, this didn't come out well, sorry about that. I knew I should have tested the fonts carefully, oh well. On top of that semantics that gives you this equational property, we have a probabilistic logic for reasoning about two different programs that gives us a way to relate the probabilities of particular events on the programs. This is called it's essentially a Hoare logic. So if you've heard of Hoare logic, we have preconditions and postconditions and a command. And the precondition describes the state of the world before you execute the command, the allowable states. You run the command, and the postcondition describes what worlds you end up in. This is very similar. The only difference is that the statements are all probabilistic. And you get a program logic for this that's derived from the semantics and really has something to do with the marginal distributions of the intermediate states that we're passing through. Okay, and again, I won't go through this, but what I want to do is tell you what it's like to use this logic to reason about cryptography. I will be honest with you. If you're a cryptographer, I hope some of you are cryptographers, you would hate this. Okay, it's very tedious and very low level, but it can be done. And in fact, we've taken something quite large, this work on searchable symmetric encryption. That was a paper that was published in 2013, and constructed a proof of security and a proof of correctness for that particular scheme. And we've also done some work on OpenSSL, just connecting the code to the actual protocol, and I'll talk about both these for just a second. So the searchable symmetric encryption, this is exciting. This is the idea that I could have a database in the cloud that's encrypted, and so the cloud provider can't know what the details of the data are. And then I could send an encrypted query to the provider, and they can compute a result and send it back, but they learn nothing, almost nothing, from that result because everything is still encrypted. So the querying, if you will, commutes with the encryption. And then when I get the result back, I can decrypt it and I can learn the answers. So that's exciting because, you know, it's a way to store data in the cloud and still be able to query it without having to trust the cloud provider. They do, by the way, they do learn something. They learn quite a bit, actually, but these schemes are interesting. This one, I think, leaks how many different things are associated with the key that you're searching on, okay? But it doesn't tell you what you return. Now, that's an information channel that you can use, but we're being honest in the assumption. Okay, so the key component in the proof and the construction of this is something called tuple sets, and I won't go into that. But this was the proof of security at a very, very high level of the tuple set security condition. And we started with the real protocol over there on the left, and then we get down to an ideal protocol that at the end shows that if we could do this, then the attacker is breaking a particular decisional Diffie-Hellman kind of assumption. So you can see there are more than about 20 different major protocols that we're writing down in this language and then proving at each step either this protocol is equivalent to that protocol or this one is very close to, that is with high probability, they have the same distributions, or in a couple of cases, actually not on this slide, sometimes we're just showing that for particular events, these are low probability events. Okay, so that, by the way, I'll show you some statistics in a second. In addition to security, we had to prove correctness of the implementation. And the security proof turned out to be actually easier than correctness in this weird case. Because if you look up there in the real to S9 step, that's part of the security proof here. So we were able to reuse a big chunk of this proof in the other proof. And that speaks to modularity and reuse in the same way that in programming languages, we want to pull out libraries of things and be able to reuse them so that we don't have to do the engineering effort to reconstruct them. Okay, so this proof had in total 58 protocols that we had to write down. It's about 14,000 lines of calc code to generate the proofs, and just even 1,300 lines of definitions to set up everything. Right, so this is probably the biggest mechanized proof of, fully mechanized proof of an encryption scheme that you'll find out there. So all this does is it shows it's possible, at least if you have somebody as smart as Adam Petcher is. Okay. Now the thing that I like about this is, unlike in traditional crypto, you don't have to trust any of that stuff. Calc will check automatically that the proofs are valid, except for the first game and the last game. You have to see that, yep, this is the protocol that we want to run, and yes, this is a problem that is infeasible for an attacker to solve. Okay, you have to look at those two. But the intermediate games you don't have to care about at all, because it's all formal. Okay, another issue is that while you can extract and run the protocol directly from the specifications that we've written down in this crypto framework, in reality, you don't want to run code generated from calc. You want to write low-level C code with efficient cryptographic routines to do things. So working with Andrew Appel, Gong's advisor, PhD advisor, there's a tool chain called the Verified Software Tool Chain where Andrew has developed a program logic for reasoning about C programs, and then using the CompCert compiler, right, we can compile that down to machine code, and as I said, we can get a refinement relation out of that machine code. So when we couple that with this crypto framework, we can actually reason about the actual code that we'll be executing on the machine. And so we've done this in the context of HMAC code within the OpenSSL library. So this is, from a cryptographic standpoint, this isn't so deep. But what's important is that we were able to actually make the full connection from the actual running x86 code all the way up to the cryptographic protocols that we're talking about. And I think that's really exciting. And I think that's where a lot of the action will be, is just connecting the formal proofs from the crypto world to the actual code. Okay, so what next? As I mentioned before, there's a lot of work that needs to be done on proof automation. Instead of writing down all these intermediate games and tediously proving that each one is connected, we really need automated tools that will take care of many of those steps for us. And that's something that one of my students is working on now. Another is that, as we saw from Spectre and Meltdown, side channels are a huge issue. Okay, and this approach does not model that at all, and in fact, it's a really big open challenge to say, okay, how do we talk about source code and the timing for that at the machine level? We don't even have good models for how much time it will take for things to run at the machine level, much less the source level. Okay, so that's a real challenge. And then there's a serious issue that as we interpret cryptographers, as we translate from English their specifications in the papers and so forth into this formal setting, there's a real chance that we'll get things wrong. And so it's vital that we get cryptographers to audit and look at those definitions to make sure that we don't have a real subtlety in the change of the definitions in what we're doing. But on the plus side, there's one thing that, that this uncovered that I don't think people appreciate about this kind of formalism, and that was the freedom to explore. So in the case of Certicrypt, Gilles Barthes was able to discover new cryptographic protocols, things that were much more efficient, because he had, basically the cryptographers were scared to try a particular variant of things. They couldn't prove it correct on pencil and paper, it was just too tedious. Gilles started from the naive thing and then developed or refined the efficient thing and proved the correctness of that transformation as he went. So I think to some degree it will help us explore, but nevertheless we need participation from the cryptographic community to really make progress on this. Okay, there's a lot of related work. I'd be happy to talk about it. One that I will mention here at the end that's very exciting is a big project out of Microsoft Research. This is called Everest. Everest is an attempt by Microsoft to recode the entire TLS stack. Right, TLS is your browser security icon as well as everything else. They're creating a whole new stack and proving the correctness of that stack all the way through. Okay, and not just, and by the way, they are addressing timing channels in what they're doing as well, at least to the degree they can. Okay, so to summarize, it's an old idea, this idea of formally reasoning about code, but I think really the tools for mechanically verifying code are starting to come to fruition, starting to make a big impact. And it's a viable way to think about, especially for security and safety sensitive code, going about getting higher assurance. All right? I actually think as students, there are lots and lots and lots of hard open problems in this space. I mentioned some of these as I went along. For example, modeling the physical environment in the context of, say, autonomous cars or autonomous drones will be a significant challenge. Even modeling hardware that we have today. Gong and I spent, how long? I don't know. Just trying to do an ISA model of the x86, and we only have a tiny fraction of that done, right? Well, he's gotten a lot more done since then. So that kind of modeling is one example of things that's really hard. Another one is modeling TCP or other real-world artifacts, and Peter Sewell at the University of Cambridge is working on that. So there's lots and lots and lots of hard open problems in here, and I hope you guys will all go off and address them. So I'll stop there, but I'll be happy to answer any questions. And let me again thank you for having me here, and that'll be it. Thanks.
So before we start the Q&A session, I'd like to have our sponsor of the distinguished colloquia to say a few words and present a gift to Greg.
Well, Greg, on behalf of my wife and my brother-in-law, Dr. Boyd Henderson, we're really pleased to be here, and what a great discussion. So thank you so much for coming to Penn State. It's interesting, Penn State and Cornell are both land-grant institutions,
Right.
and it's always great to extend and connect and create more Penn Staters. My family has 12 of them in it. And so our objective is always to have more Penn Staters if we possibly can.
Well, and we have a lot of Cornellians here.
Exactly, right. So it's really nice to see the families connecting. And you're the second leader from Cornell to have spoken here at the Distinguished Series. And it's great to see everybody here in the audience as well, because you can't have a great colloquial without both participants and speakers.
Agreed.
And on behalf of Penn State, we'd like to present you with this plaque that talks about James F. Kelly, Distinguished Lecturer. My dad was a lifelong learner, and that's why we named the series after him. And he was the guy at the kitchen table working the math problems. And I can tell by not only your talk, your work, but also the postdocs and all the people and the PhD students that you've helped, that you are dedicated to lifelong learning.
Yeah, I am. Thank you so much. I'm very honored by this.
It's our pleasure.
Yeah, appreciate it. Wow.
For questions,
Somebody has to break the seal. Yes? Great question. You might think that what we ought to do is build a proof that the proof checker checks proofs correctly. And in fact, some people have tried to work on that. There's a fundamental logical problem with that, though, that to prove the consistency of the logic that you're using to reason about things, you need a more powerful logic than the one that you're using to prove. So you run into some problems with incompleteness in that kind of setting. But we can still do a lot of it. We can do a lot of it and increase the assurance. It's somewhat ironic that these proof assistants, such as Koch and Isabel and so forth, aren't proven correct themselves. And so we should be dog fooding those things first. It's a great point. Any other questions? Trent? So one of the things that encouraged me was Adam, essentially as part of this project, basically was able to take an undergraduate crypto book and formalize it. So I think we can go that far. Now I think it took a lot of ingenuity to do this whole SSE thing. And so to the degree that we're using off-the-shelf authentication and other things, I think we can go pretty far. But when we start to get into more esoteric things, it's going to be harder. And again, it's back to what are we modeling. For example, timing is, again, a huge issue for crypto, whether you're thinking about it formally or informally. And I think that's going to be something that people will be chewing on in light of Spectre and Meltdown. So it's not a great answer. I should say in other settings, for example, reasoning about code, there's been significant progress in program logics for reasoning about code that's concurrent, that may use weak memory models, and that is essentially C-like code. So unstructured pointers in the heap and so forth. There's been some great progress over the last 10 years in logics for reasoning about that. And we're starting to see that pay off. For example, in the C++11 formalization, really the people who were formalizing that were the ones that were weighing in and saying, hey, this memory model makes no sense. Same thing with the compiler correctness people. They were coming back and saying, hey, we're not able to prove the correctness of these transformations given this memory model that you've given us. So lots of progress, but also lots and lots and lots of open problems. Yes? Yeah, so that's a great question. One of the things I like about the pain of proving right now is that it forces you to rethink the code to begin with. So I'll tell you an anecdote about something Gong and I worked on. We wanted to prove the correctness of a little checker for software fault isolation. And Google had developed such a checker. It was only a few thousand lines of code. So we thought, oh, we should be able to prove the correctness of this. Well, that code was spaghetti code. It was horrible. It was impossible to reason about. So we scratched our heads for a little while and came up with a way that really only described, we could do it in 80 lines of code. Okay, and those 80 lines were really simple because it was basically an interpreter for just a regex data table. So all of a sudden, the pain of having to prove correctness forced us to rethink. And it turned out this algorithm was not only smaller and easier to reason about, but it was much faster than Google's. So every once in a while, you get a win like that. And maybe if we get enough of those wins, that will have a big effect on the software community. The thing that I worry about is that it's really hard to change them. Like we've been trying to change the languages that people use. Like C, right, this is 1960s technology that we're still applying to build big systems. And that hasn't changed over time. Instead, we need to find tools that are compatible and layer with the existing world and focus the proof efforts on things that matter a lot, like the crypto. And ideally, we should re-architect things so that we really have a small, simple kernel that we're reasoning about and can have a lot of untrusted code running on top of it. But we're not, I don't think we're there yet. Well, I would love to say yes. I don't think it'll happen in the general world. I don't think your average Python hacker or JavaScript hacker is going to be sitting there writing proofs of correctness, right? I would love that, but I don't think it's going to happen. But I do think that people, especially people who are constructing systems on top of which we're running these applications, will have to change the way that they're doing things. And the proof will come first. The properties and the proofs will come first because they're so hard to change right now. So if we can lower, I think we need to lower the burden, the proof burden, by an order or maybe 2 orders of magnitude to get it in line with the code so that we can have the beauty of software, which is we can change it rapidly to new market conditions, new demands, meet the economic constraints, but also update the proofs rapidly. And that, I think, that's why I say there's this field of proof engineering that's emerging where we really need smart people like you folks to go chew on that and gain those 2 orders of magnitude. Yes? And I don't know, that's a great idea. I mean, I picked crypto because it's a path that we're all going through and we really depend upon it. And it's something where we all agree we need to bring expertise to bear on it. And so it's a little less controversial to say we should prove correctness of crypto than it is even your real operating system, right? And so I think that's the way we've been operating. But you're absolutely right. It'd be great to somehow have a tool that says, hey, here's where all the problems are. This is the code you need to re-architect and rethink and pull out and find a different solution for. I think architecture, by the way, is the most important of these. That we often shoot ourselves in the foot by architecting things in a way that makes it hard to do security. And re-architecting, refactoring to re-architect is a really hard laborious process, but that's the one that pays the most dividends, in my opinion. Yep. Yes. Yeah, so the question is, you know, it's fine if you're building new code to go off and prove it, but what about all this legacy code? Can we bring these tools to bear on that? And you know, generally I would say no, but there are other tools. That is, every time I think somebody's gone off to prove the correctness of something or the security, it's just too daunting a task. But they can use other tools, and we have great tools like model checkers, static analyses, other things. Generally, they enforce or are able to enforce much, much weaker properties than something like the security we're doing for the crypto. So to the degree that we can bring those automated tools to bear on deeper properties, you know, moving beyond things like memory safety to real abstract notions of isolation or confidentiality and so forth, then I think we can do it. Also, I should say languages matter a lot. So I think we can make progress by using higher level languages with things like security annotations around information flow or other things to write new systems that will be easier to apply proof methods to. So both those things. And by the way, I mean, just to encourage you, the vast majority of the code that's going to be written has not been written yet. So, you know, I think there's a lot of opportunity here going forward. Yes? Yeah, that's a great question. Question was, have I looked at machine learning and formal methods there? You know, it's a great PhD topic for somebody to dive into. What's interesting, I have done a little work on trying to model the languages that people are using for machine learning, think TensorFlow, or other stochastic languages, because it turns out they have a lot in common with the probabilistic languages that we're using to model crypto. But we really don't know what to do there at all in a formal method setting. I think there's a lot of really cool stuff like the adversarial work that's going on here, but I think we're just beginning. So if you have great ideas, I'm all ears. I'd love to hear that. The best I've heard is really kind of coming from the control theory world, where they look at, you know, sort of envelopes and switching behaviors and say, okay, as long as this thing that I don't know how it works stays within this envelope, cool. Otherwise, I'll switch to this default dumb controller that I trust and will do the right thing. So I think that framework, that's a good hack, by the way, for simplifying proofs all the time, is do some dynamic checking and then fall back on something that's simple and trustworthy as opposed to the really complicated thing that you don't understand and you don't want to prove. That happens, for example, in CompCert. They didn't want to prove the correctness of the register allocator, the graph coloring algorithm. So what they do is they just run a routine that does a graph coloring, and then they check that the thing that comes back is actually a proper coloring. And they only have to prove the correctness of the check, not the thing that constructs the color. So I think ideas like that might be applicable in that context. But it's a great problem to work on. Well, anything with machine learning is great to work on now, right? So. Actually, another one is work that Martina Body and somebody else at Google did using machine learning to generate cryptographic protocols. And the machine came up with a protocol that nobody understands, right? So, yeah. Okay, thank you so much. I really appreciate it.